So is this thing going to go away up here or what? There we go. So this is obviously a video going over the Unit 1 or Chapter 1 sample test. And let's dive right in, shall we? So these first 4 questions, you've seen these before on homework, maybe on a quiz, probably on a quiz, and of course on the sample test. There's going to be questions like this for the chapter test, where you have to check off all the different sets that each number belongs to. And at least in these times, in the year 2024, I have the real, set represented here, and I already have it checked out that they're all real. So all these numbers are real. Like I may have said in class, you're not going to be working, or you're not going to see any numbers that are not real until you get to Algebra 2 and you start talking a little bit about imaginary numbers. I'm not kidding. There's numbers that are imaginary, but you're not going to see those until Algebra 2, and it's only going to be for like half a chapter or something. So for right now, for a long time now still to come, you're only going to be working with numbers that are literally real. So all these are real, whether they're rational or irrational, doesn't matter. It all falls under the real number umbrella. But anyway, a number like -5, can you call it an integer? Yeah. Can you call it rational? Yep. And I believe that's it. Should be it. So just know what these sets are all about, really. 9.38, it's not an integer, it is rational. We can't call it a whole number, we can't call it natural, obviously it's not irrational. The number 8 belongs to the integer set, so therefore it's rational. It's also a whole number, and it's natural. Okay, in fact, like one note or one comment I could make is, if a number is natural, then it's automatically also in the whole number set, and automatically in the integer set, and automatically in the rational number set, because the natural number set is included in all of those other sets. And then square root of 13, the only set that this belongs to, other than real of course, is irrational. So maybe before we move on, just a reminder that irrational numbers, the decimals go on forever, but without a pattern, like kind of a random, irrational, crazy decimal situation. And the main types of examples that you are aware of in high school, because there's not many kinds of numbers that end up being irrational. The rational number set covers a lot of ground. So some of the main types of examples of irrational numbers only really include pi and certain square roots. So, and then rational, I hit the microphone there if you didn't hear. And then rational, that's any number that can be written as a fraction. In other words, if it has a decimal that ends at some point, like this one, or technically never even gets started, like this, or 8, you could call this 8.0, you call this -5.0. A rational number has a decimal that ends at some point, or never gets started. But if it goes on forever, see, rational number decimals are allowed to go on forever as long as they repeat an infinite pattern, like a repeating pattern forever. And again, like I said, that covers a lot of ground. And let's just move on. So I can't list any really here because there's literally an endless number of correct answers for 5 and 6 and 7. For irrational, you can put things like pi. You can put things like the square root of, oh My board's not on, so just hopefully listen, and you can. You're not too much of a visual learner, reliant. So irrational, you could put something like pi. You could put the square root of 2, the square root of 3, like so many square roots. Square root of 7, square root of 12, square root of 20, square root of 15. So most square roots that would pop into your head, most numbers, you could put as irrational. Just be careful that you're not putting like a square root of 16. Square root of 16 is actually a nice square root, like, because the square root of 16 is just like a 4 in disguise. So just be careful, because it's not all square roots that are irrational, just any square root that's a decimal, that has a decimal to it. Integers, this is like -7, -2, +2, 0, 8, 18, -18. Integers are the whole numbers, and also their negatives. So integers are still nice, but they also include negatives, like -3 or -9, as well as +3 and +9. And like I said, rational, I mean, my goodness. You could put fractions here. You could put decimals like 8.2. But you could put numbers like 7 here. You could put a number like -5, +5. There's so many different kinds of numbers you could put here. Just, of course, nothing that's actually irrational, for crying out loud. What's the opposite of 4? You need to be able to answer a question like that. You got to know what the word opposite means in math. And then you have to know what absolute value means. The absolute value of 5 is just 5, +5. And the absolute value of -7 is +7. So you have to know what absolute value is. I'll slow down here a little bit to actually remind you things like, hey, when it comes to putting a less than or a greater than or something, and by the way, yes, this is a less than, this is a greater than, and obviously this is an equal sign for, just equal to. So with fractions, my advice, if you need, is literally do on your calculator 2 divided by 3, because remember, fractions, they're like division. They're literally like division problems. So if you go on your calculator and do 2 divided by 3, it'll give you the decimal. And of course, this is -0.6 repeating. And then 1 divided by 5, that's 0.2. And then it's easier to compare decimals in general. That's generally true. It's not maybe 100% true for you, but it's generally true that it's easier to compare decimals, and then where you can tell like which one's bigger. Okay, obviously this, if maybe you didn't actually need to rewrite both of these as 0.25. Maybe you knew these were equal without doing that, but especially when you convert those to decimals, they're obviously exactly equal to each other. This one right here, 0.8 trumps 0.5, so the alligator is opening his mouth that way, so this is a greater than. And then here you just got to remember that the bigger the negative, the smaller it is. Because the more you go into negative land, the more you go left on a number line, the smaller you get. So this one's more negative, so it's smaller, and that makes, by default, this one is bigger. So -2/3 is less than -1/5. Again, negatives kind of turn the tables in that kind of way. Next in this chapter, we did some order of operations. So when it comes to all the operations here, what's the first operation you would do? You would do the division. You would do the 8 divided by 4, and that becomes 2. Everything else drops down. Then what would you do? Would you add next, or would you subtract? Hopefully you're saying you would add, because in the order of operations, whether it's PEMDAS or GERMDAS, you add and subtract like they have the same level of rank. But what breaks the tie is what happens first from left to right. So here you add and get 14, and then finally you subtract to get -3, which was never covered up, was it? Oh well. And then again, too late to cover up the 11. But so all of these operations here, what do you do first? Well, you got to do what's in grouping symbols first, which is all of that. So just focusing on all of that, what's first? What operation is first? Well, I mean, we got grouping symbols within grouping symbols. So we're going inside the parentheses, which is inside the brackets. And what do you do first? Add or an exponent? The exponent, of course. So the very first thing we're going to do is 1 to the third power. Everything else drops down as is. On a side note, not to overteach this right now, but could you have, say, done the 6 squared over here at the same time? Yeah, like I'm fully confident that you'd be perfectly fine just going ahead and saying that this becomes 36 over here. But it looks like I'm doing literally one step at a time to make a point. So what happens next? Now that you brought everything down as it was, except of course this became just 1. 1 to the third power is 1. What would you do next? Well, you're still not done with what's in the parentheses that's in the brackets. So you're going to do this 8 plus 1 to make it 9. And then after that, remember, you can always pause the video or go back and replay certain parts if I'm going too fast. But now that you're here, what do? Well, you're still not done with the brackets. You're technically done with the parentheses because now there's just a 9. There's nothing else to do in the parentheses. Okay? So now it looks like what you would do next is that, because you're technically still in the brackets. But I think you'll discover that I finally lost my patience. And I'm like, you know what? I'm just going to do the 6 squared at the same time as I do this. But technically, this comes before this in the PEMDAS or GERMDAS ranking system. Okay? So that gets us to here, because 6 squared is 36 and 2 times 9 is 18. What happens next? What operation comes next? Now that we're just down to subtracting and dividing, well, the dividing, of course, that needs to happen next. So that becomes a 2. And then finally, we can do the subtraction, which is 13 minus 2, which is 11, last time I checked. So once again, pause and go back, or just pause if as needed. But what's next, okay, might be a little bit of a plot twist, surprise out of nowhere. So check it out, people. What you would literally want to do first is that. Do not, okay, listen very carefully. Do not take any absolute value of anything until you get what's in the absolute value down to one number. So don't do the absolute value of -5 or -2. You know, make that a -7 first. Okay? -5 subtract 2 makes it -7. Then we're going to take the absolute value of -7 only once we get it down to the absolute value of just one thing, one number. And I think I actually decided, you know what? I'm just going to do this multiplication over here on the same step, because you can. You're not going to end up... It's not an actual mistake that's going to lead to a wrong answer. So I did two things at once. Sue me. It was safe. And I already took care of this. This is what would happen next before you add the 12 to get positive 19 as your final answer. Remember how when you see the word evaluate, very often you're supposed to be doing all, simplifying an expression, but at first it's got variables, but of course in the directions they don't even try to hide it. They say, oh, by the way, A is actually 3, B is actually 2, excuse me, and C is actually 6. So the very first thing you do, without making any silly mistakes, is go, well, we can substitute 2 for any B, we can substitute 6 in for any C, and we can substitute 3 in for any A. Okay? So it gets me to here, and then you're just playing the same game you were a minute ago, just following the order of operations, which looks like there's something to do in the parentheses. So that 2 minus 6 takes precedent because it's in the parentheses. All right? So that becomes a negative 4, and I did nothing else. Everything else got written as it is, as it was, as it shall be, is, was, is. Okay? So what do we literally do next? Well, I probably should have had a couple of these because there's nothing more to do in parentheses. Yes, there's parentheses here, but there's just a 6 in here. The only reason we have parentheses is to show that we're doing 5 or negative 5 times 6. And the only reason we have parentheses here still is to show that we are going to be squaring, not just 4, but negative 4, the negative included. So there's nothing to do that's in parentheses. So the P is over, or the G. Next we move on to E. Okay. So I'm probably, it's probable that we did, both this exponent, negative 4 to the second power, that makes positive 16, and 3 to the second power makes 9. What operation would be next? Well, we're not going to subtract, we're not going to add, before we multiply. So again, everything else just drops down. Got to keep your stuff organized and keep track of how this line becomes this line, and this line came from this line. Everything drops down real nice. And then what would be next? The subtraction to get, I believe, negative 14. And then finally, the addition. So I'm thinking the final answer here is negative 5. Okay? Over here, of course, after you replace the B with what it actually is in disguise, okay, what do we do first? We have division and we have multiplication. Remember, multiplying and dividing is the same rank. It's like a tie. To break the tie of which one you actually do first, what really matters is what comes first from left to right. So you have to do the division first to get negative 6, then multiply the multiplication by 2. So the final answer here should be negative 12. Once again, pause as needed. Estimate, remember, to estimate a square root, they're looking for like a decimal approximation. To get that, you're just going to go to your calculator. As far as the ones we're using here and now in the year 2024, you got to be in a mode called classic mode, so that when you type in the square root of 18, it gives you a decimal. And here, the decimal literally would go on forever if the calculator screen was infinitely, in size, if it could possibly do that. So I rounded to 2 places, okay? And then the square root of 105, once again, that's a pretty good number of places to round to. Go out 2 places before you round off and stop. So that's all you do for estimate, because estimate is another word for approximate. But with, so again, just classic mode. But with simplifying, the idea is to, like if you can't do the entire square root of 90, which you can't, not cleanly, and you can't do a clean square root of 224, maybe you can do at least some square rooting and basically be able to call it simplified. So my method that I like is, if you can look at 90 or 224 and confidently come up with the largest perfect square that you could break off as a factor, like you could break this up into two factors, the square root of something times the square root of something, as long as one of those somethings is the largest perfect square possible, like here it's 9. So if you're able to figure out the largest perfect square, you just break it off as a factor, and then you just do it. If you can do the square root of 9, you just do it, and that's 3, and then the square root of 10 just remains the square root of 10. So that's the answer. Over here, if you're able to, maybe even with the help of a calculator, there's no crime in that, but if you're able to come up with like the largest perfect square, and here it turns out to be 16. So you can rewrite this as the square root of 16 times the square root of 14. And you broke that off because it's a square root that you can do. So you do it. Square root of 16 is 4. And so this is the final answer for 22. Now before I end the video, okay, there's a pretty good chance that a lot of you in class or because this is the sample test, if you've been in class and had a chance to work on this and whatever, the other way to do these you may very well have latched onto, and you might prefer the other way. Like, it's pretty straightforward. It involves breaking down 90, for example, all the way down to its prime factors. So you make a prime factorization tree. And the good news here is, like, I think maybe one of the reasons why people might prefer this other method instead is because you don't have to stress about, oh, am I breaking it up in the perfect way? Because this was the perfect way to break up 90. This was the perfect way to break up 224. But if you're doing this other method, it doesn't matter how you start breaking up 90, because you're just going to break it down all the way anyway. So here I started with 2 and 45. There was multiple ways that you could have started off, the breakdown of 90. But 2 cannot be broken down anymore, so I'm circling it. But 45 can get broken down a little bit more into 9 and 5. And once again, 5 doesn't break down anymore because it's prime. But 9 can break down again into 3 and 3, and guess what? Now that's it. And so as a reminder, hopefully this is a reminder and you're not hearing about this method for the first time ever on the sample test. But so a reminder, hopefully, that once you get done breaking it down, any pair of numbers, like here we have a pair of 3s. So a 3 comes out, 1 3. For every pair, one of them comes out. So a pair of 3s, 1 3 comes out of the square root, and then any singles stay under the square root. Okay, now remember, I'm not sure exactly what happens over here, so just in case this doesn't really cover all the different possibilities that I'm thinking of right now, remember, if you have more than one pair, there's more than one number that comes out. If there was also a pair of 7s, then a 7 would come out with the 3 to be multiplied together. Just like here, there wasn't just a single 2, there was a single 5, and they both go underneath here and they multiply together. So this also results in, of course, what we already knew to be the final correct answer. So 224, again, there's probably numerous ways to start breaking down 224. I'm going with 8 times 28. Both of these can keep breaking down. The 8 breaks down to what? That's right, 4 times 2, and the 2 is done. 28, there's more than one way to break down 28. Maybe you, if you already did this, maybe you are following the exact same path I am, but it doesn't matter. So here I have 7 times 4. The 7 is done, but these two 4s can each break down to 2 times 2. So again, now it's just like, okay, pair of 2s. So a 2 comes out, but then, you know, if there was like a pair of 3s also, a 3 would also come out. If there was a pair of 5s, a 5 would come out. But here we happen to have another pair of 2s, so that's right, another 2 comes out. And then we still have a single 2 and a single 7. So again, that's just kind of reinforcing how, yep, 2 times 2 makes 4. That checks out. 2 times 7 makes 14. So just again, whatever way you prefer. But in all likelihood, you're going to need to show work, show at least this work, or show work like this on the test that you're going to take, you know, probably the next time I see you, in all likelihood. So good luck. Thanks for following along. Good luck on the test. Make sure you're ready.